Okay, we're going to review some stuff from first semester. And in this review, we're going to focus in on ionic compounds, how we show the structure of them with brackets and charges and things like that, and how we get to making an ionic compound. Some common names of ionic compounds and kind of the way we name ionic compounds in a systematic way, and how we write formulas for ionic compounds. Okay, we're going to start by looking at lithium and oxygen and how we can hopefully put them together into an ionic compound. So if you have a periodic table handy, that would be helpful because I'm not going to be switching back and forth to show like where something is on the periodic table. So you might have to kind of check it out on your own. So lithium starts with, well, it's in the first column of the periodic table, which means we have a shortcut that tells us it has one valence electron to start with. Okay, things in the second column have two valence electrons. We kind of skip the middle section of transition metals. We'll talk about them in a bit. Then we continue on with column 13 having 3, 14 having 4, 15 having 5, and so on and so on. With the really only exception being helium doesn't have 8, even though it's in column 18. It only has 2. Okay. Now, in order to become more stable, a neutral atom isn't really the best case scenario. Really, in order for an atom to be stable, we try and get it to kind of be like it's mimicking a noble gas, which is what we call the elements in the 18th column of the periodic table. So those noble gases in column 18 are very stable. They're like the royalty, the cool kids at the periodic table. And the way that elements mimic them is to have the same electron configuration. The easiest way to figure out if they have the same electron configuration or how to get them there is to look at how many valence electrons they have. Kind of either scooching closer to the noble gas in the same row or backing up to the previous row's noble gas. So if lithium's starting with one valence electron and we're trying to get it to be like a noble gas, we could, hold on a second. So we could try and get lithium to gain like 7 valence electrons to be like neon, 7 spots over. But that's a lot. That's a big undertaking. It would be easier as if lithium just lost 1 valence electron. It would kind of back up and be like helium, which is another noble gas. Okay, so if we just lose that 1 valence electron on lithium, it should become more stable. Okay, the short way to think it is it easier to gain valence electrons to get up to 8 or lose valence electrons to get down to 0, which is not really 0. It's some amount, from the previous energy level, but yeah, it's whatever. Okay, now losing a valence electron means that we have changed our charge. Up to this point, lithium was neutral because we had the same number of protons and electrons, but now we don't. It's an imbalance. So if we've lost a negatively charged electron, we should be becoming more positive. Kind of like if you have a lot of feelings of stress and anger, and you are able to kind of lift those from your shoulders, you feel more positive when you get those negative emotions out of there. You lose those negative emotions. So by losing a negatively charged electron, this becomes positive. And how positive it becomes depends on how many electrons are lost. If we're just losing one, each electron has a charge of -1. So we're going to have a charge of +1 without it. We kind of write it backwards as 1 plus. Okay, so that's what lithium's aiming to do to become stable. Oxygen, okay, is in column 16 of the periodic table, which means it starts with 6 valence electrons. All right. So to help it become stable, it's going to have to gain some valence electrons, and it's pretty close to having the same number of valence electrons as neon in the same row. It's just 2 away. Okay. So if oxygen could gain 2 valence electrons to get to 8 valence electrons, it could become a stable ion that way too. Okay. Most of the time when we make ions like this, we're going to end up with a total of 8 valence electrons, like starting with 6 and gaining 2 more, or starting with 5 and gaining 3 more, starting with 7 and gaining 1, starting with 2 and losing those 2 to back up to the previous noble gas. We call this the octet rule because a lot of things become more stable when they have 8 valence electrons. Octet for 8. It's not a hard and fast rule. It's more like a guideline, but it sometimes helps. kind of keep track of things. So oxygen ends up following the octet rule by gaining 2 valence electrons, gets to a total of 8 valence electrons. Okay, and it becomes negatively charged as a result. Since it's gaining 2 negatively charged electrons, it should have a -2 charge, which we write as 2 negative. Okay, now a note, we call ions specifically either a cation or an anion based on whether they are positive or negative. So when we're dealing with a positive ion, we're talking about a cation. Okay, and if we've got a negative ion, we're talking about an anion. Some ways that I remember these, okay, if you think of a cation as like, the word cat, like the animal, I'm going to give this little cat ears. Okay, so there's my cat ears. Cations are positive, like a cat has paws, it's positive. Ha ha. It's dumb, but it might help you remember it. Okay, and then for anions being negative, if you say a negative ion, there's an right there, anion, a negative ion, an ion. So hopefully that helps. So this is what we're aiming to do. We're trying to get lithium to lose an electron. We're trying to get oxygen to gain 2. So these kind of have a mutual benefit. If oxygen's looking to gain electrons and lithium has some to get rid of, they kind of have a nice little exchange they can have here that helps both of them. So we're going to show how that happens down here. Okay, so based on what we had above, we're going to show this give and take of electrons that we can use to make an ionic compound. So let's start with lithium. We're just going to write the symbol Li, and I'm going to give it 1 dot to show it's 1 valence electron. We don't really need to care about the other ones, just the valence ones. Okay, I'm going to draw oxygen here too. Oxygen started with 6 valence electrons. I'm just going to kind of go around 1, 2, 3, 4, 5, 6. All right. Lithium is looking to lose this valence electron. Oxygen needs more. So, why not make a good situation for both of them? And let's give this away to this oxygen here. Well, what happens as a result? Our lithium, as it loses that 1 valence electron, becomes positively charged. We're going to put it in brackets to show that this is kind of a completed happy ion. It's done what it was aiming to do, and we put its charge up here in the top right of those brackets. Okay, now technically you don't really need to write the 1 here. It's kind of a fashion faux pas in chemistry. So I'm going to erase that. It's kind of like writing a 1x instead of just x. You don't really need to do the 1 in front of it. It's implied. We wouldn't write the plus there if there wasn't at least 1 positive charge. So I'm just going to write plus there. Now our oxygen has gone from having its original 6 valence electrons there, 1, 2, 3, 4, 5, 6, to also having a 7th valence electron. It gained 1, but again, we're looking to gain 2 valence electrons, not just 1. So we're not quite there yet. Well, thankfully, in the world of atoms, we hardly ever just have 1 single atom of lithium and 1 single atom of oxygen to work with. We have a whole bunch of atoms of both of those elements ready to just kind of come together. So if I need another valence electron for oxygen, who's to say that there isn't another lithium atom floating around in here, Li, that has a valence electron it's trying to get rid of and can give that away to the oxygen, just like the other lithium did. Just like that. Okay, in that case, oxygen would go from having 7 valence electrons to 8 valence electrons. Okay, it gained the 2 it was looking for. It should now have a -2 charge, and we're going to put it in brackets to show this is a nice completed ion. It has become more stable. And finally, we just have to show this last lithium ion that we made in the process. All right. A good way to figure out if your ionic compound is stable and happy is to check the charges and check your valence electrons. So we should either have usually 8 valence electrons or 0 valence electrons. There's a couple exceptions, but that's usually a good tell of like, hey, everything's got 8 or 0, then perfect. Everything's happy. Everything's stable. We also want to make sure that all our charges have canceled out. If I've got a positive 1 and a positive 1 and a negative 2, that cancels out to 0. There should be no charge left over for the compound as a whole. That doesn't mean that the lithium atom is no longer positively charged. It just means that for this whole thing, made of 2 lithium cations and 1 oxygen anion, all that charge has kind of canceled out. So this whole compound is neutral. Okay. So this is our ionic compound. It's held together by this attraction between the positive and the negative and the positive. We call that ionic bonding. And altogether, that makes an ionic compound. Okay. If you have leftover charges that aren't canceling, like if we had just the positive 1 and the negative 2, we hadn't figured out this part yet, then that would show us that we've still got something else to do. Something's not happy yet. We still have charge to cancel. Otherwise, that leftover charge would still be going around and attracting to things, trying to pull in another oppositely charged ion. There's something still that has left to be done. Okay, now this compound made of lithium and oxygen has different properties. It's a different new substance. So we can't just call it, oh, it's lithium and oxygen. We need to give it its own specific name to talk about this combination of 2 lithium cations and 1 oxygen anion. So we're going to name this thing. The way that we name an ionic compound is put the cation name first, the anion name second. Okay, and if we just left it like that, then it'd just be cation, anion, like lithium, oxygen. Again, doesn't really help us. It just sounds like 2 elements. So instead, we chop the end off of the anion and make it IDE instead. All right, so the cation name stays the same. So like lithium gets to stay lithium. Oops. But oxygen, there we go, gets the end chopped off and becomes IDE at the end instead. We usually go after kind of the first hard consonant noise. So oxygen becomes oxide, IDE. So our whole name for this compound is going to be lithium oxide. We keep lithium the same, we change oxygen to oxide. Okay, and that's what we would call this compound up here if we were to give it a name. Now, if we just had this name, lithium oxide, we could say, hey, this is an ionic compound. It's got the IDE ending, okay? And we can take this and figure out this structure by putting lithium and oxygen together just like we did up here, trying to get everything happy and stable, cancel out all our charges and things like that. Now, if we wanted, though, to cut to the chase and say, I have specifically 2 lithium cations and 1 oxygen anion, we can use a formula, which just spells it out, what atoms are involved here. So in this case, I have the cation first again, just like before, just like with the name. Okay, and I have 2 lithium cations here. So I'm going to put a little 2 down here to say there's 2 lithium atoms involved in this compound. All right. And then my anion comes next, the oxygen. I have an O here. Okay, and I could put a 1. Now, kind of like the charges that we saw before, it's kind of a faux pas in chemistry to put a 1 where it doesn't really need to be. I wouldn't write the O there if there wasn't at least 1 O. If there's 2, I'm going to write 2, and if there's 3, I'm going to write 3. But if there's just 1, I don't really need to write the 1. It's kind of unnecessary. It's kind of tacky. So I'm going to get rid of that 1. So we can just call it Li2O. Now, you might be wondering, do we need the charges in this formula? Kind of like how we have in the structure. Well, no, because, again, they should all be canceled out. That's a good sign of a stable, happy ionic compound. So if we had, our charges written in here, we had our 2 positive charges from the lithium and the 1 negative 2 charge from the oxygen, those should cancel out and go away. So we really don't need those in there. We can just leave it like this. So this is our formula for the ionic compound, Li2O. So we do not need to show charges in the formula. No charges. Charges. Come on. Ah. No charges in formula. Go! Exclamation point. We can just leave it as Li2O. All right, let's try some other examples. So in this case, we already have a structure given. Now, mine is missing some dots here, but yours should already have this stuff given to you. And there's a reason for that. So let me fix this up real fast. Okay. Let me tell you why we have to have some of this stuff already kind of written out for us in this case. Okay. Chlorine on the periodic table has a little shortcut. It's in the 17th column. It should start with 7 valence electrons. Oops. I'm going to do VE for valence electrons. Okay. Which is what I've got here. I've got these 7 dots here. I've got these 7 dots here. Each chlorine has 7 valence electrons, so 7 dots. Okay. Now, copper has, we don't know, because it's in the middle of this valley of the periodic table we call the transition metals. Other metals in there along with copper, like zinc and nickel and cobalt and iron, chromium and vanadium and silver and gold. These guys are a little bit weird because they can kind of change and adapt to their situation. Depending on what they bond with and how they bond, sometimes they'll give up 2 valence electrons. Sometimes they just give up 1. Sometimes they give up 3 or 4. And some of them even give up 6 or 7. It's wacky and it's wild. So we don't have a quick and easy shortcut for figuring out how many valence electrons one of these guys is going to try and get rid of. Okay? We always need at least one piece of information with a transition metal to be able to figure out how it forms an ionic compound. Either the name or the formula or the structure. Okay, so in this case, I'm giving you the structure first. So let me finish this. In this case, copper is going to start with 2 valence electrons. That's going to give away to these chlorines. Each of them need to get 1 more valence electron to hit that octet rule to be like a noble gas. So let's move this on over here. Move this on over. If you're ever not sure of how many valence electrons something needs to gain or lose, and it's something in your first and second or 13th through 17th columns, look at the charge. So for instance, chlorine has a shortcut of having a -1 charge on our periodic table, which we see over here. Well, that means it's gained an electron, a negatively charged electron. So know that chlorine has to gain an electron somehow. So I'm gaining 1 from copper this way, and I'm not taking the other second one because I only needed 1. And in this case, I give this other electron to another chlorine atom. So it's kind of like the opposite of our lithium oxide here. Instead of giving them both to the center atom, we're giving from the center out. Okay, but again, this stuff should already be kind of on your version of the worksheet. Okay, so in this case, I'm showing off these 2 valence electrons for copper. Okay, that's the piece of information that we had to be given to be able to figure out the name and the formula for this thing. Okay, so let's start with the name. Again, we go cation first, anion second. So let's kind of just, go for it. So our cation, in this case, the positive thing is copper. It's got a +2 charge. All right. So the first part of our name is going to be just copper. That part gets to say the same. Okay. The anion in this case is chlorine. Each chlorine is an anion. It's got a -1 charge. So the other part of this name is going to be chlorine. But I'm going to chop the end off and make it IDE instead. So this is going to be chloride. So altogether, we could call this copper chloride. But that's not quite enough. And there's a reason. Okay. If I were to give you just the structure, then you could say, well, there's 2 valence electrons there and it does their thing. You can see it. Okay. If we didn't have this, if you kind of ignored the structure and I just gave you the name copper chloride, well, is copper going to give up 1 electron or 2 or 3 or 6 or what? We don't know. Okay. We need something in the name to indicate how many valence electrons this thing's going to give up, and therefore how positive this thing's going to get. We're going to use a Roman numeral in the name to say that. How many electrons they've lost, and therefore how positively charged they become. In this case, copper loses 2 valence electrons and gets a positive 2 charge. So I need a Roman numeral for 2, both for that 2 valence electrons we lost and the positive 2 charge that we get. Okay, our Roman numerals are like this. I is 1, I is 2, I is 3, IV is 4, and you can go on to more. So like V is 5 and VI is 6, but usually we don't get much higher than 4 in this class. If you ever need to know your Roman numerals and you're like, I don't know, just ask or look it up. You don't need to memorize these. You got enough stuff to worry about with the polyatomic ions in terms of memorizing. So in this case, what we need is the Roman numeral 2, which is II. We put that in parentheses right after our cation's name to say, hey, in this case, in this compound, copper is giving up 2 valence electrons. So our whole name for this is not just going to be copper chloride, but it's got to have that Roman numeral 2 in there. Can we just read that out as 2? So this is going to be copper 2 chloride. All right. So next up is writing the formula for this compound. Okay. Now, if you have the structure like we do up here, then the formula is pretty easy. We're just writing down how many of each atom we have. We put the cation first. So we have 1 copper, but again, it's kind of tacky to put the 1, so we're not going to do that. We're just going to leave it out. We have 1 copper atom. We also have 2 chlorine atoms here that make our ionic compound. CuCl with a little 2 there. Okay, just to double check all together, this ionic compound should be nice and stable because all our charge cancels out. We've got positive 2 charge, 2 negative 1 charges. So that's good. Okay, pretty straightforward. Now, where I see a lot of kind of easy to make mistakes comes from going from the name without the structure to the formula and messing up what this Roman numeral means. So I'll see a lot of people do this. They'll look at this name, copper 2 chloride, and they'll say, okay, well, that means I have 2 coppers. Or better yet, they'll write it as the Roman numeral. We'll do Cu Roman numeral 2 Cl or something like that. Okay, which, I mean, seems logical. I mean, you got a 2 there, so like, why wouldn't you have 2 there? Okay, but you got to remember that Roman numeral 2 is about how positively charged it is. Okay, our chlorine on the periodic table has to have a negative 1 charge. If there's just one of these and 2 coppers, that's not going to work. We can't have like a half a positive charge. So that's no good. Writing it like that doesn't make it any better. Okay. This does tend to throw people off because it's like, well, I feel like the Roman numeral should be in there though, because we need at least one piece of information to figure it out. Okay, we actually do already have that piece of information. We just don't need to write it as a Roman numeral, and it just takes a little bit more work. Okay, if you look at the periodic table, chlorine doesn't really have options like copper has. It's gonna be a negatively 1 charged anion. It's gonna gain 1 valence electron. So if I know this is gonna have chlorine in it with a negative 1 for each one of these, so I got negative 1, negative 1. And to make this thing happy, it's got to come out to have no charge left over. Okay, I need my copper cation to have a positive charge that cancels out this negative charge here. So I need something to cancel out this negative 2. Well, if I only have 1 copper atom to work with, that 1 copper atom has to have a positive 2 charge. Positive 2 minus 1 leaves me with 0. So if I really needed to, I could figure out that Roman numeral 2 by looking at the formula. How much positive charge do I need to cancel out the negative charge that I know these 2 guys have to have? So we don't need the Roman numeral in our formula. Okay. Let's look at a couple more examples. Write the formula of an ionic compound with the name iron 3 nitrate. So again, that Roman numeral 3 is telling us something. Okay, that means that in this case, iron is giving up 3 electrons, and it's going to end up with a positive 3 charge. I'm going to write 3 plus right there. Okay, now iron is Fe on the periodic table. So if we're writing the formula, and we know it's the positive one, I'm going to put it first. Oops. When I just lost. Oop. Come back. Sometimes my pen dies out. I have to take the batteries out and put them back in. So iron's going to come first in our formula, just like it would come first in the name. Let's see if this works. If not, I'll just have to switch to my mouse. Hey, there we go. Okay, so Fe for iron is coming first. Now, I don't know exactly how many iron atoms I have in this case yet. That's going to come down to how the charge cancels. Okay, again, it's an easy mistake to make to say, 3. I put a 3 there. But that's not what that 3 is there for. It's to say that I have a positive 3 charge. So to figure out how many Fe's I need to look at the negative charge that I'm canceling it out with. So what I'm canceling it with is this nitrate thing. Now, this kind of looks like it would be nitrogen as an anion, but if that were so, it would be nitride, not nitrate. This is a polyatomic ion, and this is why you have to be able to recognize these and know these, the formula and the charge. Nitrate is NO3, and it has a -1 charge. Okay, and that's what I'm trying to pair this thing up with. Okay, something that also can kind of get confusing. This whole thing, this whole NO3 thing has that negative charge. Okay, so I don't really care about these individual atoms, what the N has or what each O has or something like that. I don't worry about the charges they would have as ions. This whole thing together has a charge, and that is a -1 charge. Okay, so I'm going to try and pair these guys up and see if I can get them to work out. So NO3 is right here, and it has a -1 charge. Well, if I want my charge to cancel out, their charge should come out to be 0. Well, my Roman numeral is telling me that iron has a positive 3 charge in this case. So I need to figure out how much negative charge I need from this nitrate to get all that charge canceled out for this ionic compound. And I need a -3 overall. Okay, well, nitrate has a -1 charge. So if I need a charge of -3, how many nitrates do I need? Well, if each one's -1, if I had 3 of them, I'd be like saying I've got a -1 and a -1 and a -1. That cancels out to 0. So this whole nitrate thing needs to be there 3 times. Now, I can't just write the 3 after this, because then it's going to look like NO33, which is not what we're trying to say. We're trying to say that the nitrate thing, that whole thing is there 3 times. So instead, I'm going to wrap this whole thing up in parentheses. So that whole nitrate thing is there 3 times. And it's still going to look a little funky having the 3's so close to each other. But this way, this whole nitrate polyatomic ion, that whole thing is there 3 times. So you got Fe and 3 of those NO3s. Okay? Again, in the formula, we don't need to show the charges in the end. So what we're left with is just this Fe NO3 3. That's our formula for this. Okay. The last example I won't do fully, but I'll give you kind of the first bit of it, so you have kind of a place to kind of work on from. Okay, so in this case, write the name of this formula, FePO4. Well, okay, it's an ionic compound. They tell us that, so we're going to be canceling charges. It wouldn't really make sense to try and make a name with like 3 different elements all just doing their own thing, like iron phosphorus oxide. That just doesn't seem right. So far, we've only been doing examples that are kind of like one word and then another. So instead, you got to be able to recognize this PO4. is another polyatomic ion, which means it gets its own name and it altogether just has its own charge. So this PO4 is phosphorus loaded up with a bunch of oxygens. So phosphorus with oxygens. Oxygens gives us the ATE ending, so this is going to be phosphate instead of phosphorus. Phosphate. Phosphorus loaded up with oxygens. Okay, phosphate has a charge of -3. I guess I should put 3 negative. I got to be better about that. 3 negative. Okay, so I'm going to rewrite the formula down here. So a little bit better. FePO4. So this whole thing is our phosphate guy. Okay, and this whole thing has a charge of -3. Okay, so I need to figure out how much charge I need to cancel out the charge from this phosphate polyatomic ion. Now, some people might see this 4 and be like, ooh, there's 4 phosphates, so that's a charge of -12. Ooh, that's a lot. This O is there 4 times, but we just have 1 phosphate overall. This whole thing has a -3 charge. So all that we have to cancel is -3. Well, we would need a +3 charge from our iron, and we only have 1 of those. So just in total, our iron has a +3 charge. Now, you might be wondering, okay, why are we going through all this? Because, I mean, the name is just writing it out, the cation and the anion. So I put iron. Okay, and then I write, the rest of this part. Polyatomic ions are a little bit nicer to write in names because their names don't change. They don't change the IDE. Otherwise, we would confuse them. Phosphorus, as an anion, becomes phosphide. If we changed phosphate to phosphide, then it would just sound the same. We wouldn't be able to tell them apart from the name. So polyatomic ion names stay the same, just like how nitrate stays nitrate up here. Okay, but just like with the copper chloride example up here, we have to say a Roman numeral to tell us how positively charged the compound is in this case. So I can't just call this iron phosphate. I needed to figure out that the iron has a positive free charge in this case. So I can tag a Roman numeral onto it. Roman numeral 3 for its +3 charge. So the full name is not just iron phosphate, it's iron 3 phosphate. Oh, I guess we ended up doing the whole thing. I think I said we were gonna like cut it off early. I was gonna have you do the rest, but I guess we did the whole thing. So there you go. You got a free assignment basically. Hopefully this is making sense, and it's a kind of a good condensed review of some stuff we'll need to know about ionic compounds as we move forward.